Let's now add some demographic aspect to our model. Until now, we consider a model in so-called closed population, that is population in which we assume that there were no death and no natality rate. Of course, this kind of simplification may work well if you have very fast outbreaks, very fast epidemics, in which the dynamic of the epidemics is much faster than the normal demographic dynamic of a population. But for disease that tend to stay longer in a population, we need to consider the effect of the natality and the mortality in the population. It's actually quite simple to implement the model in order to consider these aspects. To add the natality rate, as you can see on the picture on the left, we just need to add a parameter that we call Ni. And then for the mortality rate, we just need to remove a portion of the people in each compartment with a parameter called mu, which is the mortality rate. The equivalent you can see into the formula. So we have a new positive factor Ni, which is the natality rate, and then we have a portion of the people in each compartment which is removed according to a rate mu. One of the most direct effect of this implementation of the model is that the R0 is now smaller when we consider the natural mortality in the population. This happens because instead of having just beta over gamma, we have beta over gamma plus mu, which means that the infectious period is a little bit shorter because people may die out before being able, by natural mortality, before being able to infect other individuals. As I said, it's important to include mortality and natality to account for epidemics that stay long in a population. These translate to the concept of endemicity. Endemicity happens when the dynamic of infectious disease is much slower than it's comparable to the natural demographic dynamic of the population. And so, if the epidemic has a R0 below 1, the outbreak dies out and the pathogen disappears from the population. But if the R0 is above 1, this means that the pathogen will always stay in the population. It will never die out because there will always be new susceptible people to infect due to the natality rate. Practically, this may create a situation called the endemic state, which mathematically is defined with this formula. In this case, we are assuming that natality rate and mortality rate are the same, just to simplify our calculations. In the endemic state, on average, we will have a proportion of susceptible individuals which is equal to 1 over R0. The proportion of infectious individuals will be equal to mu, the mortality rate, over beta multiplied by R0 minus 1. And then the proportion of recovered individuals, which again we consider as immune, will be just the totality minus the other two factors. So 1 minus the proportion of susceptible and the proportion of infectious individuals. Let's make an example. Let's now take a population with an average life expectancy of 80 years old. It's easy to calculate the mortality rate, it's just 1 over the life expectancy. And then we take a beta equals to 1.87, 89, 1.8, 1.9, and a gamma of 1 over 8. That is a disease that in which the infectious status is more or less 8 days. These numbers imply R0 more or less 14, which is in the range of measles, which we know is a very infectious disease. Using these parameters, we see that the steady state predict that a really small portion of the population will be susceptible in any point in time or infected, while most of the population will be recovered and therefore immune. Or we can say it will be seropositive if we have a disease with lifelong immunity with measurable lifelong antibodies like measles again. So we can see that these numbers confirm what we know for childhood disease like measles, in which most of the population will have the antibodies. If we instead evaluate a disease which is much less infective, like flu, I choose some parameters in order to have R0 of around 1.3. We see that at the steady state, most of the population will be naive for the pathogen, or even less, and very few people will be infected in every point in time, and also a small part of the population will be immune. This tells us how that disease with very high R0 will be consistent and stable in the populations, and this will produce the situation in which most of the population will have encountered the virus in their lives. The consequence of this of the endemicity is that we can estimate the mean average of infection given the R0. You can see here that it's pretty simple to calculate the mean age of infection with this formula. So the mean age is equal to 1 over the mortality rate multiplied by R0 minus 1. And from this formula, it's easy to notice that the age of infection, that is the age in which a person on average encountered the pathogen for the first time in their life, decreases as R0 increases, because R0 is at the denominator. And this is also clear in this plot on the right. So as the basic reproductive ratio or number increases, the mean age at which a person encountered the pathogen decreases very fast. We can see that for measles, again, which is more or less 14, which has R0 of more or less 14, the age of first encounter is lower than 10 years. From this formula, we can also estimate R0 using the age of first encounter and the life expectancy. As I said before, life expectancy is 1 over mu. This is very useful because sometimes calculating R0 using beta and gamma is not so easy, but for disease in which you have lifelong immunity and lifelong antibodies that you can measure through seroprevalence studies, you can calculate R0 using the formula. Again, by using the parameters that I showed you in the previous slide, for measles, we can show that the mean average of infection is very low, it's 6.3 years. So on average, children will encounter measles at an age of more or less 6 years. But if we apply the same formula to a much less invasive disease like flu, then this number grows exponentially. In this case, it's 300 years. Which is a little bit absurd because this is a simplified formula for simplified models, but also may mean that some people will never encounter the disease in their whole life. But the endemicity status is not something constant and stable through time. When a new disease is introduced in a population, the endemicity status is reached through oscillations. You will see that if you do prevalence studies about an infectious disease that is endemic, you will it's possible to notice that there will be oscillatory periods of a few years maybe, in which the prevalence is increased and then increasing and decreasing. And this is due to the fact that when you introduce the pathogen, most of the population get infected very fast, but then the number of susceptible is not enough to sustain the infection, and so we have the prevalence that goes down very fast. But then as new people are born, thanks to the natality rate, the compartment of susceptible is replenished again, and so the infection has a new individual to infect, and so we can have a new outbreak. So sometimes people may confuse random outbreaks in a population with the natural course of endemic infection. For example, these parameters here are again much similar to measles in reality, and they predict a period between peaks of 2.43 years, which is more or less comparable to what observed for measles. To calculate this period, there is a simple formula: 2 by p Greek multiplied by the square root of the average age of infection, and d, which in this case is the average length of the infectious period, which consider both the natural infectious period of the disease plus the natural mortality. One last point about this kind of models: if instead of considering mu as the natural mortality of the disease, we consider it as the mortality due to the disease, so it's applied just to the I compartment, we can notice that people have a competing outcome. They may either survive and recover or die from the disease. And this allows us to compute the so-called survival rate, which is simply gamma, which is the normal course of the disease, over gamma plus mu, which is the infectious-related mortality rate. Conversely, if we take the complementary of this, we can get the case fatality rate, which is mu over gamma plus mu.